Hi scholars, this presentation is on comparative designs in single-case research. Three main objectives are 1. Describe components of multi-treatment designs. 2. Describe components of alternating treatment designs. 3. Describe components of adapted alternating treatment designs. This presentation will also include a description of the parallel treatments design. Four main features of comparative designs are that they adhere to baseline logic, which involves the repeated measurement of behavior through direct observation across two adjacent conditions. Each case serves as their own control. Replication is essential to documentation of experimental control. Data can be visually inspected for trend, level, variability, overlap, consistency, and immediacy of effect. 3 demonstrations of effect at 3 points in time are needed to document a functional relation. When using comparative designs, first identify literature that demonstrates the effectiveness of both interventions or treatments. Then move forward in making a comparison of competing interventions, comparison of intervention innovations, comparison to refine interventions, or comparison with contextual variables. Comparative designs are vulnerable to threats of multi-treatment interference, which include carryover effects and sequence effects. Sequence effects occur when the order of treatment influences performance. Carryover effects occur when characteristics of one condition influence the other. To control for multi-treatment interference, we need to select behavior sets of equivalent difficulty. But since we are making a comparison by applying 2 or more interventions to the same behavior, the ultimate levels of behavior cannot be attributed to only one intervention. Thus, we have a separation of treatments issue. This is not a critical threat when the comparisons are made between 2 interventions that have been shown to be effective in isolation. Nevertheless, we should name this in our limitations section. Let's first examine multi-treatment designs. This design is flexible. It allows for comparison between 2 treatments in addition to comparison between baseline and one treatment. The multi-treatment designs are often used when an a priori comparison is planned. The multi-treatment designs extend from the AB-AB design by allowing for comparison between 2 treatments in addition to comparisons between the baseline and one treatment. The simplest extension uses a BC-BC sequence. That is, if you conduct an AB-AB investigation and B fails to initially show a sufficient effect, then you can add C to conduct the ABC-BC design. This design bears relevance when a research question to the effect of does intervention B produce better outcomes than intervention C is posed. You can demonstrate experimental control for the B to C comparison. However, you cannot demonstrate experimental control for evaluating the effects of B or C in relation to the initial baseline condition. But if you introduce ABA, BCB, then you can answer the questions. Does intervention B produce changes in behavior in comparison to baseline A? And does intervention C produce superior behavior change compared to intervention B? Another modification of the AB-AB is to add a component to the intervention and then evaluate with and without that component. For example, A, BC, B, BC. Multi-treatment designs allow us to see consistent difference in trend or changes in level to make comparisons between 2 interventions. The designs require a reversible behavior. That is, behaviors that are likely to change readily based on the context. For example, so-called problem behavior or social interactions, rather than on learning. When using multi-treatment designs, try to include at least 3 students so that you can counterbalance the order of treatments to reduce the threat of multi-treatment interference. For example, you might test AB-CBC for one student and AC-BCB for another student. Stability within conditions is important for making a causal inference. To recap, when you use a multi-treatment design, first identify reversible behavior. You can opt to use a pre-treatment baseline, and you must stick to the determined order of conditions. You can only make comparisons between adjacent conditions. Pause to think about this. Which interventions can be compared in order to demonstrate experimental control? To summarize, the multi-treatment designs are used to compare different interventions. It is best to practice counterbalancing the order of interventions. And the designs require one reversible behavior. Another comparative design is the alternating treatments design. The alternating treatments design is used to compare interventions. It is procedurally similar to the multi-element design, which is used when the objective is to assess factors that may be maintaining so-called challenging behavior. With this design, two treatments are applied to the same reversible behavior. We determine the order of conditions ahead of intervening and include rapid alternation of conditions across days or within a day across sessions. The major threats to internal validity is multi-treatment interference, which includes sequence and carryover effects. Counterbalancing and rapid alternation are the best steps to take to guard against these threats. Rapid alternation is required, and participants must also be able to discriminate between treatments. Within the alternating treatments design, we counterbalance treatment order, and we counterbalance extraneous variables as well. Stable data are not required with the treatment condition. That is, some variability is permissible as long as there's low overlap between conditions. We look for the data paths to separate so that we can recommend the best condition. Simonson and colleagues compared 3 conditions to evaluate the teacher's use of self-monitoring of praise statements: no intervention, count using a counter, and tally putting a tally on a sheet. They determined that the rate of self-praise, praise per minute, was best in the count condition. To record rate data in alternating treatments, teachers were asked to estimate the number of times they praised on a 0 to 4 times per minute scale. In this graph, data show that the researchers also included baseline or pre-treatment and follow-up phases to descriptively explore the effects of self-monitoring across time. Results indicate that noting each instance of specific praise by either tallying or using a counter resulted in optimal performance, and teachers preferred using a counter. Another comparative design is the adapted alternating treatment design. This design is particularly useful for comparing the efficiency of 2 instructional strategies. The design is used with non-reversible behaviors, which means we can evaluate acquisition of functional, academic, or developmental behaviors. The adapted alternating treatment requires 2 or more behaviors, which can be reversible, but need to be independent and functionally similar. As in the use of the alternating treatments, participants must also be able to discriminate between conditions. The order of conditions needs to be counterbalanced. For example, A-B-C-B-C for one student and A-C-B-C-B for another student. It's ideal to conduct 2 sessions per day, alternating the treatment. The use of a pre-treatment baseline is part of the adapted alternating treatments design. The adapted alternating treatment should be conducted where the number of sessions is consistent across treatments. The analysis allows for an evaluation of a consistent difference in trend and level so that the optimal treatment can be identified. Adapted alternating treatments design was developed to compare instructional practices with non-reversible behaviors, specifically those that are not in the participant's repertoire, that are independent, and that are functionally equivalent. To use this design, researchers must select behavior sets or chains of equivalent difficulty. One way to ensure that behaviors are of equal difficulty is to teach the behavior to non-participants who have similar attributes to those who will be recruited as study participants. The same procedure should require the same amount of instruction to establish criterion level responding. Another way to ensure that behaviors are of equivalent difficulty is to select behaviors from pools of responses for which norms exist. For example, oral reading fluency norms for number of words correct per minute, math computation or math concepts and application norms for percentage of correct responses. A third method is to conduct a logical analysis of the difficulty of responses and discrimination required to perform correctly. A fourth method is to evaluate performance on related behaviors. Any of these methods can be combined, and time should be planned to ensure that behaviors are of equivalent difficulty. The threats to internal validity are the same as in the use of alternating treatments. Multi-treatment interference in the form of sequence effects, where the order of treatment influences performance, and carryover effects, where characteristics of one condition influence the other. These threats are respectively controlled with rapid alternation and counterbalancing conditions. Unlike in the use of multi-treatment or multi-element designs, separation of treatments is a non-issue. In Schlosser and Blischak's adapted alternating treatments, the effects of speech and print feedback on spelling performance were evaluated. 4 children with autism and no functional speech were taught to spell words with a speech-generating device under 3 feedback conditions. In the auditory visual condition, children received both speech and print feedback, whereas in the auditory and visual conditions only, 1 type of feedback was provided. All 4 children reached criterion across conditions, although 3 children reached criterion first with print or speech print feedback. 1 child was most efficient with speech print followed by speech feedback. The final comparative design included in this presentation is the parallel treatments design. Parallel treatments design is useful for comparing instructional practices with non-reversible behaviors. Conceptually, the design employs 2 multiple probe designs that operate concurrently. We need 2 distinct instructional strategies to compare, 1 per multiple probe. Another way to conceive of the design is 3 time-lagged adapted alternating treatment designs. The challenge with this design is selecting behaviors. You need 3 or more independent behaviors of equal difficulty and functional equivalence per intervention. That is 6 in total. There are a few examples of this design in print. The one selected here is from 2000. Puffpath and colleagues evaluated interventions to improve spelling for adults with intellectual disability. To select 6 independent behaviors of functional equivalence and equivalent difficulty, researchers generated 3 word sets per intervention, traditional and modified orthography. Data were collected on the spelling accuracy for both approaches intermittently during the A condition and continuously during treatment. The design allows for the researcher to detect separation of data paths when comparing the effects of the 2 interventions, and also allows for the demonstration of effect to be replicated across word sets and potentially across participants. For comparative designs, the 6 components of visual analysis hold as relevant: level, trend, variability, overlap, immediacy of effect, and consistency across similar conditions. However, we also look for and evaluate the magnitude of separation, the consistency of separation, and at least 4 comparisons are needed to establish experimental control. Let's try applying what we've learned to what we already know by practicing writing a research question for an alternating treatments design. Is there a difference in the percentage of 10-second intervals with social initiation under intervention B compared with intervention C? First, let's note that we are comparing the effects of 2 treatments, intervention B and C, on a reversible behavior, social initiation. The 4 components of the falsifiable research question are independent variable, dependent variable, direction of change, and functional relation. Is there a functional relation between intervention B versus intervention C on the percentage of 10-second intervals with social initiation for preschool children with autism spectrum disorder? Let's evaluate the experimental control on a 1 to 7 scale where 1 is low and 7 is high. We can rate this 7 because there is a very clear separation of data paths. The magnitude of that separation is strong, there is no overlap, and we see more than 4 demonstrations of that separation. Here we could say a 6 out of 7. There is a clear separation. The magnitude of that separation is not as strong as we saw in the previous graph. There are more than 4 demonstrations. We could call this 5 out of 7. There becomes a clearer separation of data paths as time passes on, and we do see that magnitude of separation maintained and even expanding with more than 4 data points. This one we would call a 3 out of 7 because that magnitude of separation doesn't maintain across more than 4 data points. The paths overlap. Here is a 1 out of 7. It's difficult to visually inspect and determine which is the superior treatment because of the high degree of overlapping data points. So reflect on your learning related to the objectives. Describe the components of multi-treatment, alternating treatment, and adapted alternating treatment designs. Small is beautiful. According to B.F. Skinner, as quoted in Kurlinger and Lee, it is more useful to study one animal for 1,000 hours than to study 1,000 animals for 1 hour.